inequality and some of the example for orthonormal systems. So basis inequality. This we have already discussed in your linear algebra class. Like basis inequality says that a theorem for any orthonormal system EI I greater than or equal to 1. That means we are having an infinite system. That is in previous case we have said that if this is the notation means I is running from 1 to infinity. So EI subset of H, and for every x belongs to H we have sigma I greater than or equal to 1. Now inner product modulus of inner product of x EI square is less than or equal to norm of x square. So this we want to prove. And we call this inequality as Bessel's inequality. Let us see how we can prove this. So consider yn is equal to sigma I equal to 1 to n. We are taking finite case here, and we will approximate as n tends to infinity to the infinite case. So consider yn equal to sigma I equal to 1 to n xei inner product of xei times ei. Then we find what is the modulus of inner product of yn with x. So it should be less than or equal to norm x into norm yn. This follows from Cauchy-Schwarz inequality. Now yn x, that's equal to, you can write that in yn x as sigma 1 to n, the first part yn inner product with x. Okay, that can be reduced as sigma 1 to n xei square. Inner product of xei modulus of that square times the summation. We got that means we consider that part. Sigma 1 to n xei into ei into x. Now this is equal to sigma. Okay, if you want means you can expand also. So first I am doing without expansion, and next I will do the expansion of the summation. Okay, so sigma I equal to 1 to n inner product of xei is constant into vector part is eix. So I will get eix. Now from this we have, last class we have discussed one lemma. If this is the case, it should be equal to sigma I equal to 1 to n modulus of inner product of xei square. So we have used the previous one result. In terms of this is given as alpha. In your result it is given as alpha, and this is given as some vector. Then we are having the summation is equal to modulus of alpha times square. Okay, that was the result. Now we can also prove this by just expanding. We want to have inner product of ynx. So ynx, substitute what is ynx. So ynx, if you are substituting, you will get ynx is equal to x e1 into e1 plus etc plus x en into en comma x. Now take the linearity. That means this is a constant, and this will become e1 into x, sorry, inner product of e1 x plus inner product of x e2 into inner product of e2 x etc plus inner product of x en into inner product of en x. Now this everything will become x e1 x. So it is x1 e1 square type. So here this plus its conjugate type, right? Can you follow? It is of set into set bar form. So that is nothing but modulus of z square. So we can use modulus of x e1 square plus etc plus modulus of x en square. That is nothing but summation I equal to 1 to n modulus of x ei square. So we got that quantity. Now hence sigma I equal to 1 to n modulus of inner product of x ei which is less than or equal to norm x into inner product summation uh, having 1 to n square will become for mod yn square. So 1 to n inner product modulus of inner product of x ei square all thing raised to 1 by 2. Okay, so we have used this quantity. Therefore sigma 1 to n modulus of x ei square all thing raised to 1 by 2 is less than or equal to x. Have you got that one? So here find what is norm of yn square. Okay, exactly it will come as less than or equal to norm of x into norm of y terms. So what is norm of yn square? Norm of yn square is inner product of yn with yn. So substitute for yn. Now this is equal to sigma 1 to n inner product of x ei into ei with inner product sigma 1 to n x ei ei. Now expanding this we get the linearity condition. So x e1 into e1 will come. That has to take inner product with this quantity. So E1 here only resulting it should be E1. So it is x E1 into x E1x plus etc. So you get that's equal to sigma I equal to 1 to n a norm of x ei all square. That only we have used here. Now we have proved the result for finite case. So finite n we have proved this. Now taking n tends to infinity, we get this quantity is less than norm x. So hence the result. Now corollary 2.1.5. For any x belongs to H and any orthonormal system EI from 1 to infinity, there exists a y belongs to H such that y equal to sigma I equal to 1 to infinity x ei times ei. We want to take a y such that. So consider yn equal to sigma 1 to n x ei ei. Now by previous corollary, limit n tends to infinity, sigma I equal to 1 to n, inner product of x ei with ei is equal to sigma I greater than 1, that means I equal to 1 to infinity x ei into ei. It easily follows. The limit of that yn is our y. Now some examples of orthonormal systems. So what was orthonormal systems? We will say that a system is orthonormal if each of its members modulus should be equal to 1 and there will be mutually orthogonal. So consider in L2 the vectors En equal to 0, 0, 0 is coming, 1 is coming in the nth entry. Okay, if this is a system, then it is an orthonormal system. Evidently, its norm is equal to 1. Since we are going for the supreme norm, norm is equal to 1. Okay, and when you're taking inner product with any of E1 and E2, we will get it as 0. Now consider in L2, capital L2 minus pi comma pi. Consider the vectors of the form 1 by root 2 pi e raised to int, where n is running from minus infinity to infinity. What about this case? When you're finding is norm, so norm of 1 by root 2 pi e raised to int, that's equal to, in L2 the norm is defined as integral minus pi to pi modulus of 1 by root 2 pi into e raised to int dt square dt. You can take this quantity outside, so you get 1 by root 2 pi square will come. So yeah, pi square will come, and here you will get integral root 2, oh sorry, not root 2 pi, root 2 pi only will come. Okay, so 1 by 2 pi integral minus pi to pi into modulus of this thing is 1. E raised to int modulus is 1. So 1 dt will come. That's equal to 1 by 2 pi into integration of 1 is t. T between the limit minus pi to pi. That's equal to 1 by 2 pi into pi plus pi. So pi plus pi you will get 2 pi. Cancelling 2 pi and 2 pi you will get 1. So what you proved is norm of every term of this quantity is 1. Now for orthogonality, we want to prove that if you are taking any two numbers, their inner product is 0. So I'm taking for 1 and 2. 1 and 2 is just for our verification only, and we will prove for the general case. Okay. So 1 by root 2 pi e raised to it, 1 by root 2 pi e raised to 2 it. So when I am finding its mm, inner product should be integral minus pi to pi 1 by root 2 pi e raised to it into e raised to minus 2it dt. That's equal to 1 by 2 pi integral minus pi to pi e raised to minus it dt. That's equal to minus 1 by 2 pi I e raised to integral of e raised to minus it is minus e raised to minus 1 by pi into e raised to minus it will come. So this will become minus 1 by 2 pi I into e raised to minus it between limits minus pi to pi. That's equal to minus 1 by 2 pi I into e raised to minus I pi minus e raised to I pi. Now e raised to I pi is cos pi plus I sin pi. So cos minus pi will come minus cos pi plus I sin pi. So you get minus 1 by 2 pi I into cos pi minus I into sin pi. So sin pi is 0, and here cos pi minus cos pi will come. It will get cancelled. So 0, 0 will come. So entire thing will become 0. This just for our verification only. I have performed the inner product of the two terms, but we want to prove it in general. So in general case, we can take n and m belongs to Z and consider 1 by inner product of 1 by root 2 pi e raised to int, 1 by root 2 pi root of 2 pi, right? Root of 2 pi e raised to imt, that's equal to integral minus pi to pi e raised to int into 1 by root of 2 pi e raised to minus imt dt. Okay, minus will be minus has come because we are taking uh, integral a to b x y bar dt. Okay, so that's equal to 1 by root of 2 pi is common, so you can take that outside, so it will become 1 by 2 pi. So 1 by 2 pi integral minus pi to pi e raised to I into n minus m into t dt. So this is equal to 1 by 2 pi I into n minus m. That's equal to this constant term I have taken outside, because when you are doing for integration of this part, you will get e raised to I of m minus 1 into t whole divided by m minus n minus m into I. So that I have combined with this I. Okay, so I into m minus 1 to e raised to I into n minus m into t between minus pi to pi. Now n m belongs to z, so it can be taken as some kt. So 1 by 2 pi I into, okay, n minus m into e raised to I kt between the limit minus pi to pi. So I have missed here some k, so I should write k. So now it become 1 by 2 pi, sorry, some problem with this tool. Let me check it. Okay, here when k will be the, so anyway it won't affect our result, since we are getting e raised to I k pi minus e raised to minus I k pi. So it will become, sine term will become 0. Only remaining is cos k pi minus cos of minus k pi. So cos k pi, you'll get minus 1 raised to k minus of minus 1 raised to minus k will come. Cos of minus theta is cos theta, since cos is an even function. So anyway the result will be 0. Here also I missed that k. So here is coming some n minus m now. So that n minus m I should incorporate here and here also. So hence we get this system is an orthonormal system. We have proved that norm of the system is equal to 1 and any two members of the system are mutually orthogonal. Next we will consider one more system that I am leaving for you to work. L2 minus pi comma pi, consider the vector 1 by root 2 pi cos nx by root pi comma sin nx by root pi for n equal to 1, 2, 3, etc. This will also form an orthonormal system. So we can check this the same way as we have done in second example that I am leaving for you to check it. And if you are having any difficulty, please post your doubt, or what you need further clarification, means just post your comments. Okay, I'm closing today's session. Thank you for your patient listening.